The Panther tank sat motionless on the proving grounds outside Kubinka, 25 miles west of Moscow, on a cold morning in September 1943. Senior Engineer Lieutenant Colonel Nikolai Shashmurin of the Scientific Research Institute No. 48 walked slowly around the massive vehicle, his breath forming clouds in the autumn air. 3 months earlier, this particular Panther had been part of Germany's elite Grossdeutschland Division during Operation Citadel at Kursk. Now it belonged to the Soviet Union, one of several captured examples being systematically examined to understand why the Germans had designed what appeared to be a masterpiece of engineering that somehow kept breaking down. Shashmurin had spent 15 years designing and testing tanks for the Red Army. He had examined captured German equipment since 1941, from the early Panzer IIIs to the formidable Tiger. But the Panther represented something different, something that troubled him in ways he was still trying to articulate to his fellow engineers. The Germans had studied captured T-34s after the shock of encountering them in 1941. They had analyzed Soviet design philosophy. Then they had apparently learned all the wrong lessons and created a tank that was theoretically superior in almost every measurable way, yet somehow performed worse in actual combat conditions. The story of how the Panther came to exist begins with the German invasion of the Soviet Union on June 22, 1941, and the absolute shock German tank crews experienced when they first encountered the T-34 medium tank in combat. German panzer divisions had swept across Poland, France, and the Balkans, facing opponents whose tanks were either obsolete designs or poorly deployed. The Wehrmacht's combination of Panzer III and Panzer IV tanks, supported by superior tactics and coordination, had achieved victories that seemed to validate German armored doctrine. Then, German forces crossed into Soviet territory and everything changed. The T-34 model 1941 was unlike anything German tankers had faced. Its sloped armor was effectively impervious to the standard German 37mm and 50mm anti-tank guns at normal combat ranges. Its 76.2mm main gun could penetrate German tank armor from distances where German tanks couldn't effectively fight back. Its wide tracks distributed weight effectively, allowing it to cross soft ground and mud that stopped German tanks. Its diesel engine was more resistant to fire than gasoline engines and provided excellent range. Most troubling of all, Soviet factories were producing them in quantities that German intelligence had considered impossible. General Heinz Guderian, one of Germany's premier armored warfare experts, wrote in his memoirs about the first encounters with T-34s during the advance toward Moscow. The appearance of the T-34 at the front, he noted, represented the most unpleasant surprise of the entire campaign. German tank guns were useless against its frontal armor. The only effective weapons were the 88mm anti-aircraft guns pressed into anti-tank service, and these were too few and too cumbersome for mobile warfare. Something had to be done immediately, or German armored forces would find themselves outclassed and outnumbered by Soviet tanks. German response initially focused on improving existing designs. The Panzer IV, originally intended as an infantry support tank with a short-barreled 75mm gun, was upgunned with a long-barreled high-velocity weapon and given additional armor. This created the Panzer IV AUSF-G and subsequent variants that could fight T-34s on relatively equal terms. The Tiger heavy tank was rushed into production with an 88mm gun and massive armor protection that made it nearly invulnerable to Soviet weapons. But these were interim solutions or specialized vehicles for specific roles. What German High Command wanted was a completely new medium tank that could replace the Panzer III and IV as the Wehrmacht's primary armored fighting vehicle. This tank would need to match or exceed the T-34's battlefield performance while incorporating German engineering standards and manufacturing quality. The specifications issued to German tank manufacturers in November 1941 reflected lessons learned from 6 months of combat against Soviet armor. The new tank would mount a high-velocity 75mm gun capable of defeating T-34 armor at long range. It would have sloped armor similar to the T-34 to maximize protection. It would weigh approximately 35 tons to maintain reasonable mobility. It would use a powerful engine to provide excellent speed and range. 2 German firms, Daimler-Benz and MAN, submitted competing designs. The Daimler-Benz proposal was radical, essentially a German copy of the T-34, featuring a rear-mounted engine, front-drive sprocket, and dramatically sloped armor. It looked so similar to the T-34 that German soldiers might have difficulty distinguishing it from Soviet tanks at distance. The MAN proposal was more conventionally German in layout, with a front-mounted transmission, rear engine, and heavy armor protection. After extensive evaluation, the German Army Weapons Office selected the MAN design in May 1942, designating it the Panzerkampfwagen WAV Panther. The decision to reject the Daimler-Benz design in favor of the more conventional MAN proposal revealed something fundamental about German military culture and engineering philosophy. The Daimler-Benz design would have been faster to produce because it simplified many aspects of tank construction by copying proven Soviet solutions. But German engineers and military officials simply could not accept the idea of copying a Soviet design, even one that had proved devastatingly effective in combat. German tanks had to be engineered to German standards, incorporating German technical sophistication, regardless of whether this sophistication actually improved battlefield performance. The Panther that emerged from this decision-making process was in many ways a magnificent piece of engineering. Its sloped frontal armor was 80 millimeters thick at 55 degrees from vertical, providing protection equivalent to approximately 140 millimeters of vertical armor plate. This made the Panther's frontal arc essentially immune to the standard Soviet 76.2 millimeter tank gun at normal combat ranges. The side armor was 45 millimeters thick, less than frontal protection, but adequate against most anti-tank weapons when angled properly. The turret armor reached 100 millimeters on the front and featured a highly effective mantlet design that deflected most hits. The main armament was the 75 millimeter KWK-42 L-70 gun, one of the finest tank guns developed during the entire war. With a barrel length 70 times the caliber, it achieved muzzle velocities of nearly 1,000 meters per second with standard armor-piercing ammunition. This gave it the ability to penetrate 120 millimeters of vertical armor at 1,000 meters range, more than sufficient to defeat any Soviet tank from the front at combat distances. The gun's accuracy was exceptional, thanks to German optical quality and fire control systems. Experienced Panther crews could achieve first-round hits at ranges exceeding 1,500 meters under good conditions. The Maybach HL-230 engine provided 700 horsepower, giving the Panther a theoretical maximum speed of 46 kilometers per hour on roads and reasonable cross-country mobility, despite its weight, which had grown to 45 tons during development. The interleaved road wheel suspension system, similar to that used on the Tiger, distributed weight effectively and provided a smooth ride that improved gunnery accuracy while moving. On paper, the Panther appeared to be everything German designers had intended, a tank that combined T-34 battlefield lessons with superior German engineering and manufacturing quality. Production began in January 1943 at MAN's factory in Nuremberg, with additional production starting at Daimler-Benz and MHN factories shortly afterward. The initial production target called for 250 Panthers per month, a rate that would allow the Panther to quickly replace older medium tanks in Panzer divisions. Adolf Hitler took personal interest in the Panther program, viewing it as the weapon that would restore German armored superiority on the Eastern Front. He demanded that Panthers be ready for the summer offensive planned against the Kursk salient, a massive operation that would employ nearly 3,000 tanks and assault guns in an attempt to encircle and destroy Soviet forces. The rush to get Panthers into combat for Operation Citadel proved catastrophic. The first Panthers rolled off production lines in January 1943, but they were essentially prototypes being manufactured. Normal testing and development that would take 18 months was compressed into weeks because Hitler demanded Panthers be available for the summer offensive, mechanical problems that would normally be identified and corrected during development instead plagued the first production vehicles. Engine fires were common, transmissions failed with alarming frequency, final drives broke down, fuel pumps malfunctioned. These weren't minor teething problems, but fundamental design flaws that should have been corrected before mass production began. By May 1943, approximately 250 Panthers had been produced, but fewer than 200 were operational. The rest sat in repair facilities having various mechanical issues corrected. German tank commanders who would lead the Kursk offensive expressed serious concerns about committing untested vehicles to the most important operation of the year. Guderian, now Inspector General of Armored Troops, recommended delaying the offensive until Panthers were properly developed and crews adequately trained. Hitler rejected this advice, insisting the offensive proceed in early July, while weather conditions were favorable and before Soviet defenses became stronger. Operation Citadel began on July 5, 1943, with German forces attacking from both north and south toward the Kursk salient. The southern pincer, led by Field Marshal Erich von Manstein's Army Group South, included 2 full Panther battalions assigned to Grossdeutschland Division and the elite LSSAH Division. These units fielded approximately 200 Panthers between them, representing nearly the entire operational Panther inventory. What happened to these tanks over the following week would shock German commanders and validate every concern that had been raised about rushing them into combat. Before the first shot was fired, Panthers began breaking down during the approach march to assembly areas. Transmissions overheated and seized. Final drives cracked under the stress of the tank's weight. Engines caught fire due to fuel system leaks and inadequate shielding of hot exhaust components. By the time Grossdeutschland Division reached its jump-off positions on July 4th, only 184 of its 200 Panthers remained operational, and this was before encountering any enemy action whatsoever. The division's after-action reports described a trail of broken-down Panthers stretching back dozens of kilometers, each one requiring recovery and repair. When the offensive began on July 5th, Panthers advancing across open terrain toward Soviet defensive positions performed brilliantly in their intended role when they worked properly. The 75mm gun proved devastatingly effective against Soviet T-34s and KV-1 heavy tanks, achieving kills at ranges where Soviet return fire was ineffective. The frontal armor shrugged off hits from 76.2mm guns that would have destroyed earlier German tanks. Panthers that reached Soviet positions and engaged in direct combat often achieved impressive kill ratios, with some individual tanks claiming 5 or more Soviet vehicles destroyed. But they kept breaking down, not from battle damage but from mechanical failures that removed them from combat far more effectively than Soviet fire. Transmissions failed with catastrophic regularity, leaving Panthers immobilized in the middle of battlefields. The interleaved road wheel suspension, so effective at distributing weight and providing a smooth ride, proved impossible to maintain under field conditions. Mud and debris packed between the overlapping wheels, and when temperatures dropped at night, this debris froze solid, completely immobilizing the tank until crews spent hours chipping away ice. The Maybach engine ran so hot that fuel lines and seals failed, causing fires that destroyed tanks without any enemy intervention. By July 10th, 5 days into the offensive, Grossdeutschland Division reported only 41 Panthers operational out of the 200 it had started with. The rest were either destroyed by enemy action, broken down awaiting repair, or had suffered catastrophic mechanical failures requiring complete engine or transmission replacement. The LSSAH Division's Panther Battalion reported similar catastrophic readiness rates. German recovery and repair units worked frantically to return broken Panthers to service, but new breakdowns occurred faster than repairs could be completed. The entire Panther force that was supposed to spearhead Germany's most important offensive of 1943 had essentially ceased to exist as a combat-effective formation in less than a week. Soviet forces defending the Kursk salient noted the appearance of the new German tank with considerable interest. Frontline reports described a tank larger than the Panzer IV with a powerful gun and heavy frontal armor that proved difficult to penetrate. But these same reports also noted that many Panthers appeared abandoned with no battle damage, suggesting mechanical problems were removing them from combat. Soviet recovery teams made capturing intact Panthers a priority, understanding that examination of this new threat would be critical for future operations. The first relatively intact Panther was captured on July 12th near Prokhorovka during the massive tank engagement that marked the climax of the Southern Offensive. A Panther from the LSSAH Division had advanced too far ahead of supporting forces and suffered a track break from a Soviet anti-tank mine. The crew, unable to repair the damage under fire, and with Soviet infantry approaching, abandoned the vehicle after attempting to destroy it with demolition charges. The charges damaged the interior, but left the hull, turret, engine, and transmission largely intact. Soviet engineers arrived within hours to begin recovery operations. Moving the disabled Panther proved immediately challenging. At 45 tons, it was significantly heavier than the T-34's 32 tons, and Soviet recovery vehicles struggled with its weight. The first attempt using a single recovery tractor failed when the tractor's winch cable snapped under load. Eventually, 3 recovery vehicles working together managed to pull the damaged Panther onto a heavy transport trailer for movement to rear areas. This difficulty in recovery operations itself represented valuable intelligence about one of the Panther's operational vulnerabilities. The captured Panther reached the Scientific Research Institute No. 48 at Kubinka in early August 1943. This facility, established in 1931, served as the Soviet Union's primary center for examining captured enemy equipment and testing new Soviet designs. Its staff included some of the Soviet Union's most experienced tank designers and engineers, men who had created the T-34 and KV series and who understood both the theoretical principles and practical realities of armored vehicle design. They approached the Panther examination with professional interest and some apprehension, knowing this tank represented Germany's response to Soviet armor and might incorporate solutions to problems they themselves had struggled with. Senior Engineer Lieutenant Colonel Shashmurin led the examination team, supported by specialists in armor metallurgy, automotive engineering, weapons systems, and fire control. Their directive from the main Auto Armor Directorate was comprehensive. Determine the Panthers' strengths and weaknesses, assess whether Soviet forces needed similar capabilities, evaluate whether captured technology should influence Soviet designs, and identify vulnerabilities that could be exploited tactically. The examination would take months and produce a detailed technical report that would influence Soviet tank development for the remainder of the war. The examination began with external inspection and measurement. Soviet engineers carefully documented every dimension, armor angle, and design feature. The Panther's glacis plate immediately drew attention. At 80 millimeters thick and sloped at 55 degrees, it was theoretically more effective than the T-34's 45 millimeter plate at 60 degrees. Soviet engineers calculated that the effective thickness against perpendicular impacts exceeded 140 millimeters, making it essentially immune to the 76.2 millimeter F-34 gun that armed the standard T-34. This was concerning from a combat perspective, but also represented validation of the sloped armor principle that Soviet designers had pioneered with the T-34. However, the engineering team immediately noted something peculiar about the armor construction. Rather than using a single rolled plate welded into position like Soviet practice, the Panther's glacis was constructed from interlocking plates welded together at complex angles. This provided no additional protective benefit, but significantly complicated manufacturing. Soviet engineers estimated that producing the Panther's hull required at least 50% more welding time than a comparable T-34 hull. Why would German engineers choose a more complicated construction method that provided no tactical advantage? The answer became apparent when examining the overall design philosophy. German engineers had prioritized theoretical perfection over manufacturing simplicity. Every aspect of the Panther reflected this approach. The interlocking armor plates allowed precise control of angles and thicknesses, but required skilled welders and extensive quality control. The interleaved road wheel suspension provided excellent weight distribution and ride quality, but required hundreds of additional parts and complex assembly procedures. The precision-engineered transmission delivered smooth gear changes but demanded manufacturing tolerances measured in hundredths of millimeters. Soviet engineers spent considerable time examining the Panther suspension system because it differed so dramatically from Soviet practice. The T-34 used large road wheels on independent torsion bar suspension, a system that was relatively simple to manufacture, easy to maintain, and robust enough to withstand the punishment of combat operations. The Panther used overlapping and interleaved road wheels in a design borrowed from the Tiger, with torsion bars positioned perpendicular to the hull rather than longitudinally. This provided exceptional ride quality and distributed the tank's weight across a larger ground contact area. But the complexity was staggering. Each side of the Panther featured 16 small road wheels arranged in 8 overlapping pairs. The wheels were mounted on swing arms connected to torsion bars, and the entire system was incredibly tightly packed in the lower hull. Removing an inner road wheel for replacement required first removing up to 5 outer wheels, a process that could take several hours even under ideal workshop conditions. In field conditions with limited tools and spare parts, road wheel maintenance became nearly impossible. Soviet engineers tested this by simulating combat damage to an inner road wheel and then attempting to replace it using only the tools and equipment that would be available to a field maintenance crew. The process took 6 hours and required 3 experienced mechanics working together. By comparison, replacing a damaged road wheel on a T-34 took less than 30 minutes with 2 men. The Soviet examination report noted dryly that the Panther suspension system appeared to have been designed for peacetime conditions where tanks would be maintained in well-equipped workshops rather than for wartime conditions where repairs must be made quickly in field environments under enemy fire. The mud and ice vulnerability that German crews had discovered at Kursk became immediately apparent when Soviet engineers tested the suspension under simulated winter conditions. They drove the Panther through muddy terrain and then allowed the mud packed between road wheels to freeze overnight. The next morning, the tank was completely immobilized with frozen mud locking the overlapping wheels together. Clearing the ice required hours of work with crowbars and blowtorches. Soviet engineers calculated that a Panther battalion operating in winter conditions would need to dedicate several hours each morning simply to freeing suspension components before tanks could move, assuming appropriate tools and heating equipment were available. The engine examination revealed both impressive engineering and fundamental design flaws that helped explain the high breakdown rates at Kursk. The Maybach HL-230 was a 23-liter V12 gasoline engine producing 700 horsepower, significantly more powerful than the T-34's 500 horsepower V2 diesel. The engine featured advanced technology including aluminum alloy construction for weight savings, sophisticated fuel injection, and high compression ratios for efficiency. German engineering quality was evident in every component, with precision manufacturing and careful tolerances throughout. But the engine ran extremely hot, and cooling was marginal at best. Soviet engineers started the captured Panther's engine and operated it under various load conditions while monitoring temperatures throughout the engine compartment. Within 20 minutes of operation at high power settings, temperatures near the exhaust manifolds exceeded 500 degrees Celsius. Fuel lines running near these hot areas were protected only by thin metal shielding that proved inadequate. The rubber seals and hoses used throughout the fuel system deteriorated rapidly when exposed to these temperatures, leading to leaks that created serious fire hazards. The air filtration system proved grossly inadequate for Eastern Front conditions. The Panther used multiple small air filters that required frequent cleaning, unlike the T-34's large oil bath filter that could operate for extended periods in dusty conditions. Soviet engineers tested the Panther's air filters by running the engine in dusty conditions similar to those encountered on Russian steppes in summer. The filters clogged completely within 2 hours, and when engineers dismantled the engine afterward, they found significant dust contamination in the cylinders. Continued operation under such conditions would rapidly destroy the engine through premature wear. The transmission examination provided perhaps the most revealing insights into why Panthers broke down so frequently. The Panther used a sophisticated synchro-mesh gearbox similar to those found in high-performance civilian automobiles, with 7 forward gears and 1 reverse gear. This transmission, designated AK-7 represented German precision engineering at its finest, featuring hardened gears, precise gear tooth profiles, and smooth synchronization between gears. In a passenger car operating under normal conditions, it would have been a superb piece of machinery. But the transmission was fundamentally inadequate for a 45-ton combat vehicle operating under battlefield conditions. Soviet engineers calculated that the AK-7 was designed for a vehicle weighing perhaps 35 tons maximum, and adding 10 tons of additional weight during Panther development had pushed it beyond its safe operating margins. The gears and shafts were simply too small to reliably handle the torque required to move the Panther's mass, particularly when starting from rest or climbing slopes while fully loaded with ammunition, fuel, and crew. To verify this assessment, Soviet engineers conducted stress tests on the transmission by operating the Panther through a series of starts, stops, turns, and slope climbs while monitoring internal components with specially installed sensors. The measurements showed that gear teeth were experiencing stress levels approaching their material limits during normal operation, and any additional strain from difficult terrain or combat maneuvering pushed them into the plastic deformation range where permanent damage occurred. Soviet engineers concluded that transmission failure was not a possibility, but an inevitability given the operating conditions the Panther would face in combat. The final drive assemblies proved even more problematic. These components, which transmitted power from the transmission to the drive sprockets that moved the tracks, were manufactured to extremely tight tolerances and required precise assembly. The gears inside the final drives were relatively small despite transmitting enormous torque, and they required constant lubrication to prevent overheating and rapid wear. The lubrication system used multiple small oil passages that were prone to clogging, and any interruption in oil flow caused catastrophic failure within minutes. Soviet engineers tested a final drive to destruction by deliberately restricting oil flow and operating under load. The final drive failed completely after only 40 minutes, with gear teeth literally shattering from thermal stress and inadequate lubrication. When they dismantled the failed unit, they found that the small oil passages had partially clogged with normal wear debris, reducing oil flow to the point where components couldn't stay adequately lubricated under heavy loads. German technical documents captured with the Panther showed that final drives were supposed to be inspected and serviced every 150 kilometers of operation, a maintenance interval that would be impossible to maintain under combat conditions. The comparison to Soviet design philosophy became stark when examining how Soviet engineers had approached similar technical challenges. The T-34's transmission was crude by German standards, with unsynchronized gear changes that required skill to operate smoothly. But it was massively over-engineered for reliability, with large gears and heavy-duty shafts that could withstand tremendous abuse. Soviet designers assumed that transmissions would not receive perfect maintenance, that crews would miss gears and grind synchros, that tanks would be operated by minimally trained drivers under combat stress. Every component was designed to survive mistreatment and continue functioning. The T-34's final drives were similarly overbuilt, with large gears and generous lubrication passages that could tolerate some neglect without immediate failure. Maintenance intervals were deliberately set at levels that could realistically be achieved by field maintenance crews with limited tools and spare parts. Soviet engineers accepted some inefficiency and crudeness in exchange for reliability and ease of maintenance, understanding that the best engineered tank was worthless if it couldn't be kept running under combat conditions. The Panther's main armament and fire control systems proved to be areas where German engineering superiority was undeniable. The 75mm KWK-42 L-70 gun was magnificently accurate, with a sophisticated recoil system that minimized barrel movement and returned the gun precisely to its original position after firing. The gun sight was a precision optical instrument providing excellent magnification and clarity. The turret traverse mechanism used hydraulic power for smooth, precise movement that improved first-round hit probability dramatically compared to manually traversed turrets. Soviet engineers tested the gun system extensively, firing at targets at various ranges and comparing performance to Soviet 76.2 mm and 85 mm guns. The Panther gun's accuracy exceeded Soviet weapons significantly, particularly at longer ranges where its flat trajectory and high muzzle velocity made range estimation less critical. At 1,500 meters, the Panther gun achieved first-round hit probabilities, nearly double those of the T-34's gun, a decisive advantage in tank-versus-tank engagements where whoever fired accurately first would likely win. But Soviet engineers noted that this technical superiority came with significant drawbacks. The sophisticated fire control systems required extensive crew training to operate effectively, training that many German tank crews pressed into service to replace combat losses would not receive. The precision optical systems were fragile and required careful maintenance to keep properly aligned. The hydraulic turret traverse system was vulnerable to battle damage and required specialized repair parts that might not be available in field conditions. Once again, German engineers had prioritized theoretical performance over practical battlefield reliability. The armor metallurgy examination produced perhaps the most surprising findings. Soviet engineers conducted extensive testing on armor samples cut from various locations on the captured Panther, including ballistic testing against different ammunition types and metallurgical analysis of the armor composition and heat treatment. The results revealed that while German armor was excellent in some respects, it suffered from problems that Soviet armor had already solved through different metallurgical approaches. German armor plate used high-hardness steel that provided excellent resistance to penetration when struck at appropriate angles. The hardness was achieved through complex heat treatment processes that required careful control of temperatures and cooling rates. This worked well for armor plates that could be properly heat-treated in large industrial furnaces, but the complex shapes and welds required in tank construction created areas where proper heat treatment was impossible, and these areas were significantly weaker than surrounding material. Soviet engineers conducted ballistic tests specifically targeting welded joints in the Panther's armor. They found that shots that hit near welds were significantly more likely to penetrate or cause catastrophic cracking than shots that hit the center of armor plates. The problem was that German armor, while very hard, was also relatively brittle compared to Soviet armor that used different heat treatment processes to maintain some ductility along with hardness. When German armor failed, it tended to crack catastrophically rather than deforming plastically like Soviet armor did. The examination report included a detailed comparison of German and Soviet armored steel metallurgy, explaining why Soviet designers had deliberately chosen slightly lower hardness in exchange for better ductility and resistance to catastrophic cracking. This represented a fundamental philosophical difference. German engineers optimized armor to resist penetration under ideal test conditions, while Soviet engineers optimized armor to survive the messy reality of combat, where hits occurred at weird angles. Multiple hits struck the same area, and welds and complex shapes were unavoidable. After 3 months of intensive examination, Soviet engineers compiled their findings into a comprehensive report submitted to the main Auto Armor Directorate in November 1943. The report's conclusions were striking in their candor and their implications for Soviet tank development. The Panther, the report concluded, represented a tank designed by engineers who understood theoretical principles excellently, but who had insufficient practical understanding of combat conditions and manufacturing realities. It was, in many ways, a masterpiece of engineering that was also a practical failure as a combat vehicle. The report identified specific areas where German engineers had made decisions that prioritized sophistication over reliability. The transmission and final drives were fundamentally inadequate for the vehicle's weight and operating conditions, and no amount of careful maintenance could prevent eventual failure under combat stress. The suspension system provided excellent performance when working properly, but was too complex to maintain under field conditions and had catastrophic vulnerabilities to mud and ice. The engine ran too hot and required too much maintenance for battlefield conditions. The armor, while effective, was more brittle and vulnerable to cracking than Soviet armor using different metallurgical approaches. Most significantly, the report concluded that the Panther represented validation of Soviet design philosophy rather than a superior alternative requiring emulation. Soviet engineers had deliberately chosen simplicity, reliability, and ease of manufacture over technical sophistication when designing the T-34, understanding that numbers of operational tanks mattered more than individual vehicle performance. The Panther examination proved this approach correct. A technically inferior T-34 that remained operational and could be quickly repaired was vastly more valuable than a technically superior Panther that spent half its time broken down awaiting spare parts that might never arrive. The report made specific recommendations for Soviet tank development based on the Panther examination. Soviet designers should continue prioritizing reliability and manufacturability over technical sophistication. The T-34 platform should be upgraded with improved guns to counter the Panther's armor, but fundamental design philosophy should remain unchanged. Any new Soviet tank designs should incorporate lessons learned about what not to do from the Panther examination, rather than attempting to copy German engineering approaches. The sophistication that made German tanks impressive in controlled tests made them unsuitable for the brutal realities of sustained combat operations on the Eastern Front, where tanks had to keep running despite inadequate maintenance, undertrained crews, and minimal spare parts availability. The recommendations specifically addressed the question of whether Soviet tanks should adopt German-style features like interleaved suspension, complex transmissions, or precision fire control systems. The answer was a clear no across the board. Soviet tank production in 1943 exceeded German production by enormous margins, precisely because Soviet tanks were designed to be manufactured quickly by workers with limited skills using relatively crude production equipment. Adding German-style complexity would reduce production numbers without providing proportional combat advantages, a terrible trade-off given that the war would ultimately be decided by which side could field more operational tanks. Soviet designers took these recommendations seriously when developing upgrades to existing tanks and when designing new vehicles. The T-34-85, which began production in early 1944, incorporated a larger turret and an 85mm gun capable of defeating Panther armor at reasonable combat ranges. But the chassis, engine, transmission, and suspension remained essentially unchanged from the original T-34 design, maintaining the reliability and ease of manufacture that had made the T-34 so successful. Soviet engineers could have designed a more sophisticated tank, but they chose not to because sophistication for its own sake provided no combat advantage. The heavy tank program that would produce the IS-2 similarly incorporated lessons from the Panther examination. Soviet designers needed a heavy tank capable of defeating German heavy armor while remaining reliable enough for sustained operations. The IS-2 used a powerful 122mm gun that could destroy any German tank with a single hit, but its automotive components emphasized reliability over sophistication. The transmission was manually operated without synchronizers, crude by German standards, but virtually unbreakable under combat conditions. The suspension used large torsion bars and road wheels, similar to those on the T-34, components that had proven themselves in extensive combat service. The impact of the Panther examination extended beyond Soviet tank development to influence tactical doctrine and training. Soviet tank crews received specific instruction on Panther vulnerabilities discovered during the examination. The side armor was much thinner than frontal armor and could be penetrated by 76.2 mm guns if tanks could maneuver for flank shots. The transmission and final drives were vulnerable components, and mobility kills could be achieved by targeting the lower front plate where transmission damage would immobilize the tank. The engine compartment was prone to fires, and incendiary ammunition aimed at the rear deck could potentially cause catastrophic damage even without penetrating armor. Soviet anti-tank gun crews received similar training on Panther vulnerabilities. The 76.2 mm guns that were standard Soviet anti-tank weapons in 1943 couldn't reliably penetrate Panther frontal armor, but they could defeat side armor at reasonable ranges. Anti-tank gun deployment doctrine emphasized positioning guns to enable flank shots rather than frontal engagements where Panther advantages would be decisive. The examination findings directly influenced how Soviet forces fought against Panthers throughout the remainder of the war, turning theoretical knowledge about vulnerabilities into tactical advantages. German commanders slowly came to understand that the Panther program had significant problems, though they never fully grasped how fundamentally flawed the design philosophy was. After the Kursk disaster, where most Panthers broke down before achieving anything significant, German ordnance departments made numerous modifications attempting to improve reliability. The engine cooling system was redesigned with better shielding for fuel lines. The air filtration system was improved. Transmission components were strengthened. These modifications helped, but couldn't address the fundamental problem that the entire vehicle was over-engineered for sophistication rather than designed for reliability. Panther reliability did improve somewhat over time as production experience accumulated and the most serious problems were corrected. By late 1944, Panthers were somewhat more reliable than the disaster of Kursk, though they never approached the reliability of simpler designs like the T-34 or American Sherman. German tank units developed extensive maintenance procedures specifically for Panthers, dedicating significantly more maintenance time and resources to keeping them operational than was required for earlier Panzer models. This maintenance burden reduced the number of tanks available for combat at any given time because more were always in repair shops. The production numbers told a revealing story about the practical consequences of design complexity. Germany produced approximately 6,000 Panthers during the entire war, despite enormous investments in production facilities and resources. By comparison, the Soviet Union produced over 35,000 T-34s of various models during the same period. The United States produced nearly 50,000 Sherman tanks. German engineers created a tank that was theoretically superior in many ways to Allied designs, but they couldn't produce it in quantities sufficient to matter strategically because it was too complex to manufacture quickly. Soviet intelligence continued tracking Panther deployment and performance throughout 1944 and 1945, collecting after-action reports from units that encountered Panthers and examining additional captured examples when possible. These reports consistently showed that while Panthers were dangerous opponents when they worked properly and were handled by experienced crews, they continued suffering from mechanical reliability problems that removed many from combat before they ever encountered enemy forces. The percentage of Panthers operationally ready on any given day rarely exceeded 60% and often dropped below 50% during sustained operations. The winter of 1944 to 1945 proved particularly devastating for Panther reliability. The suspension problems that Soviet engineers had identified during their 1943 examination became catastrophic when Panthers operated in the brutal cold and deep snow of the Eastern Front winter. Frozen mud between interleaved road wheels immobilized entire units for hours each morning. The complex transmission systems became sluggish in extreme cold, and failures increased dramatically. German maintenance crews found themselves spending more time keeping Panthers running than actually employing them in combat, a situation that only worsened as spare parts became increasingly scarce due to Allied bombing of German industry. Soviet tank crews who encountered Panthers in combat during 1944 and 1945 developed considerable respect for the vehicle's capabilities when it was working properly and handled by skilled crews. The 75mm gun could kill T-34-85s from ranges where Soviet tanks couldn't effectively fight back, and the frontal armor remained largely immune to 85mm fire at longer ranges. But Soviet tankers also learned that Panthers were vulnerable from the flanks and rear, that they were prone to breaking down during extended operations, and that aggressive maneuvering could force Panthers into situations where their advantages didn't matter. The tactical doctrine that emerged from Soviet experience fighting Panthers emphasized mobility and numbers over technical sophistication. Soviet tank units would attempt to engage Panthers from multiple directions simultaneously, accepting losses from the superior German gun and armor in exchange for flank shots against weaker side armor. Soviet numerical superiority meant they could afford to trade 2 or 3 T-34s for one Panther and still come out ahead strategically, especially since destroyed T-34s could be replaced quickly while destroyed Panthers could not. German veterans who fought in Panthers during the war and survived to write memoirs generally praised the tank's firepower and armor protection while acknowledging its serious mechanical problems. Hans von Luck, who commanded Panther-equipped units in Normandy, wrote that when Panthers worked properly, they were magnificent weapons that could dominate any battlefield. But he also described the constant frustration of planning operations around assumed Panther availability, only to discover that half his battalion was broken down with transmission failures or engine problems. The gap between theoretical capability and actual operational availability made force planning extremely difficult. Otto Carius, one of Germany's most successful tank aces who transitioned from Tigers to tank destroyers, wrote that he preferred the simpler Panzer IV to the technically superior Panther specifically because the Panzer IV was more reliable and easier to maintain under field conditions. Carius understood that a technically inferior tank that remained operational was infinitely more valuable than a superior tank sitting in a repair shop awaiting parts that would never arrive. His perspective validated exactly what Soviet engineers had concluded during their 1943 examination. The post-war assessment of the Panther by military historians and technical experts has been mixed, acknowledging both its impressive capabilities and its serious flaws. The gun and armor were undeniably excellent, providing capabilities that Allied tanks struggled to match until very late in the war. The fire control systems and optical quality gave German crews significant advantages in long-range gunnery. But the mechanical reliability problems, manufacturing complexity, and resource requirements made it a strategic failure despite tactical successes. Soviet engineers who had examined captured Panthers wrote in post-war technical journals about the lessons they had learned from German engineering approaches. They praised German attention to detail and theoretical knowledge while criticizing the fundamental disconnect between engineering sophistication and practical battlefield requirements. Soviet design philosophy that prioritized simplicity, reliability, and ease of manufacture had proven correct through practical combat experience. A crude tank that worked was superior to a sophisticated tank that didn't, a lesson that would influence Soviet military vehicle design for decades. The Panther examination influenced American tank development as well, though less directly than it influenced Soviet designs. American engineers examined captured Panthers that were shipped to Aberdeen Proving Ground in Maryland for evaluation. American conclusions were similar to Soviet findings. The Panther was an impressive piece of engineering that was too complex for its own good. American tank design philosophy already emphasized reliability and ease of maintenance, and the Panther examination validated this approach rather than suggesting American designers should adopt German sophistication. The development of the American M26 Pershing heavy tank, which began entering service in early 1945, reflected lessons learned from examining German tanks, including the Panther. American designers created a tank with heavy armor and a powerful 90mm gun capable of defeating Panthers, but they deliberately kept the automotive components relatively simple and reliable. The Pershing used a proven transmission design, straightforward suspension, and an engine that prioritized reliability over maximum performance. It was a competent rather than spectacular tank, but it worked reliably under combat conditions. The fundamental lesson that emerged from the Panther examination and from combat experience was that tank design required balancing numerous competing factors, and engineers who optimized for any single factor at the expense of others created vehicles that underperformed in actual combat. The Germans had optimized for firepower, armor protection, and technical sophistication, while underemphasizing reliability, ease of manufacture, and maintainability. Soviet designers had made different choices, deliberately accepting some technical crudeness in exchange for reliability, manufacturability, and ease of maintenance. The numbers demonstrated which approach worked better under actual wartime conditions. By late 1944, Soviet tank units typically had 80–90% of their T-34s operationally ready on any given day. German Panther units rarely exceeded 60% operational readiness and often dropped much lower during sustained operations or in difficult weather. This readiness gap meant that Soviet units could sustain offensive operations for longer periods and could deploy more tanks in any given engagement, despite Panthers being technically superior on a tank-for-tank basis. The industrial implications were equally significant. Soviet factories could train relatively unskilled workers to produce T-34 components in a matter of weeks. The simple design meant that production could be dispersed across numerous factories, making the tank program less vulnerable to disruption from bombing or ground combat. German Panther production required skilled workers and sophisticated manufacturing equipment, making it vulnerable to Allied strategic bombing and difficult to expand rapidly when casualties demanded replacement vehicles. The resources required to maintain Panther units in the field exceeded those required for simpler tanks by enormous margins. Each Panther required approximately twice as much maintenance time as a Panzer IV, and 3 times as much as a T-34 based on German and Soviet maintenance records. Spare parts consumption was similarly higher, and many specialized parts could only be manufactured by specific suppliers whose facilities were increasingly targeted by Allied bombing. The logistical burden of supporting Panther units meant fewer resources available for other critical needs like fuel, ammunition, and general supplies. German tactical doctrine evolved to accommodate Panther limitations rather than fully exploiting Panther capabilities. Tank units learned to plan operations, assuming significant numbers of Panthers would be non-operational at any given time. Maintenance schedules became increasingly elaborate, with Panthers requiring extensive servicing after relatively short operational periods. German commanders learned to position repair facilities close to front lines because Panthers often couldn't travel long distances to rear area repair depots without suffering additional mechanical failures en route. The crews who operated Panthers developed love-hate relationships with their vehicles. When working properly, the Panther provided firepower and protection that made crews feel nearly invincible in combat. The ability to engage and destroy enemy tanks at ranges where return fire was ineffective gave German tankers significant psychological advantages. But the constant mechanical problems created enormous frustration and stress. Crews never knew when their tank would suffer a catastrophic transmission failure or engine fire that would leave them vulnerable and immobile in the middle of a battlefield. Training new Panther crews became increasingly difficult as the war progressed and Germany's situation deteriorated. The complex fire control systems and driving controls required extensive training to operate effectively, training time that simply wasn't available when units needed immediate replacements for combat losses. Inexperienced crews struggled with both combat tactics and vehicle operation, often making mistakes that caused mechanical damage or reduced the Panther's effectiveness in combat. The T-34's simpler systems meant Soviet crews could be trained to basic proficiency much faster, another advantage that numerical superiority amplified. The Panther's legacy in post-war tank development was mixed and complicated by Cold War politics and differing interpretations of what lessons should be drawn from its combat history. Western tank designers generally concluded that the Panther represented a cautionary tale about over-engineering and the importance of reliability. Soviet designers viewed it as validation of their design philosophy and continued emphasizing simplicity and reliability in post-war tanks like the T-54 and T-55. German engineers who had worked on the Panther and survived the war ended up working for various countries' defense industries, bringing their technical knowledge but often having learned lessons about the importance of reliability from the Panther's failures. Modern historical assessments of the Panther acknowledge it as one of the most influential tank designs of World War II, despite its flaws. The combination of sloped armor, powerful high-velocity gun, and relatively mobile platform established a template that influenced tank design worldwide for decades. But these same assessments also note that the Panther's mechanical unreliability and manufacturing complexity made it less effective than its specifications suggested, and that simpler Allied tanks ultimately proved more successful strategically despite being tactically inferior in direct combat. The story of Soviet engineers examining a captured Panther at Kubinka in 1943 encapsulates fundamental truths about weapon system design that remain relevant decades later. Technical sophistication matters far less than reliability when equipment must function under the stress and chaos of actual combat. Manufacturing complexity reduces the numbers of weapons that can be produced, and numbers often matter more than individual quality. Design decisions must account for realistic maintenance capabilities and spare parts availability, not ideal conditions that rarely exist in wartime. These lessons, learned by Soviet engineers through meticulous examination of German engineering, influenced military vehicle design throughout the Cold War and continue influencing design philosophy today. The Panther examination also illustrated important points about engineering culture and how it influences weapon system development. German engineering culture emphasized precision, sophistication, and theoretical perfection, values that produced magnificent machines under ideal conditions, but fragile systems under battlefield stress. Soviet engineering culture emphasized robustness, simplicity, and practical functionality, producing crude machines that worked reliably under terrible conditions. Neither approach was inherently superior, but for total war involving millions of troops operating over vast territories, the Soviet approach proved more effective. Lieutenant Colonel Shashmurin, standing in front of the captured Panther on that September morning in 1943, understood something that would take German commanders years to fully appreciate. The Panther represented everything wrong with German approaches to armored warfare. Brilliant engineering applied without sufficient attention to practical requirements. It was a tank designed by engineers who loved engineering for its own sake, rather than as a means to an end. The T-34 that Shashmurin had helped develop was crude by comparison, but it won the war because it could be produced in enormous numbers, maintained by barely trained crews, and kept running under conditions that left Panthers broken down and useless. The Germans had studied captured T-34s and learned the wrong lessons, copying some superficial features while missing the fundamental design philosophy that made the T-34 effective. They created a tank that looked similar to the T-34 in some respects, but embodied completely opposite engineering principles. Where the T-34 was simple, the Panther was complex. Where the T-34 was robust, the Panther was fragile. Where the T-34 could be produced quickly and maintained easily, the Panther required enormous resources and constant attention. Soviet intelligence reports from late 1944 and early 1945 tracked Panther deployment numbers and noted with satisfaction that German Panther production was consuming resources that could have produced larger numbers of simpler tanks. Each Panther required approximately the same steel, labor, and manufacturing capacity as two Panzer IVs, but provided less than twice the combat effectiveness and far less than twice the operational availability due to mechanical problems. German commanders had requested thousands of Panthers, believing they would turn the tide on the Eastern Front, but the actual impact was disappointing relative to the investment. The final irony was that by the time German engineers had corrected most of the Panther's serious mechanical problems through endless modifications and improvements, the strategic situation had deteriorated to the point where tank quality no longer mattered. Allied numerical superiority was so overwhelming by late 1944 that even perfectly reliable Panthers couldn't have changed the war's outcome. German industry simply couldn't produce enough tanks of any type to replace combat losses while simultaneously dealing with strategic bombing, resource shortages, and general industrial collapse. Soviet tankers who fought through 1945 and reached Berlin encountered Panthers occasionally, but found them increasingly irrelevant to battles being decided by massive Soviet numerical superiority and comprehensive air support. The technical sophistication that German engineers had worked so hard to achieve mattered little when Soviet units could afford to trade 5 tanks for 1 and still advance. The T-34s that Soviet engineers had deliberately kept simple and crude were still running and fighting while Panthers sat abandoned along German roads with broken transmissions and empty fuel tanks. The captured Panther at Kubinka remained there after the war, preserved as a museum piece and training aid for Soviet tank designers. Generations of Soviet engineers studied it as an example of what not to do, how not to design military equipment. The sophisticated systems that German engineers had been so proud of became cautionary examples in Soviet technical schools. Students learned about the interleaved road wheels that provided excellent ride quality, but couldn't be maintained under combat conditions. They studied the precision transmission that performed beautifully when new but failed catastrophically under sustained use. They examined the complex fire control systems that required extensive training and constant maintenance. The Panther examination of 1943 and the lessons learned from it represented a turning point in Soviet understanding of armored warfare and weapon system design. Soviet designers had believed their T-34 approach was correct, but German tank quality early in the war had created doubts. The Panther examination removed those doubts completely. Soviet design philosophy emphasizing simplicity, reliability, and ease of manufacture was validated by the Panther's failures, despite its technical sophistication. This validation influenced Soviet military vehicle design for the remainder of the Cold War and beyond. Modern tank designers still study the Panther as a case study in engineering trade-offs and the importance of reliability in military systems. The vehicle is simultaneously celebrated for its impressive firepower and armor, while criticized for mechanical unreliability and manufacturing complexity. It represents a warning about the dangers of prioritizing technical perfection over practical effectiveness, a lesson that remains relevant as military systems become increasingly complex and sophisticated. The story that began with Soviet engineers examining a captured Panther in September 1943 ultimately became a story about competing visions of what made an effective weapon system. The German vision emphasized technical excellence and sophisticated engineering. The Soviet vision emphasized practical effectiveness and operational reliability. Combat experience demonstrated that under wartime conditions with mass armies and limited resources, the Soviet approach worked better despite producing less impressive individual weapons. This lesson, learned by examining enemy equipment captured in combat, influenced military thinking far beyond tank design and far beyond World War II. Senior engineer Lieutenant Colonel Nikolai Shashmurin retired from Soviet military service in 1955 after a career spanning nearly 3 decades of tank design and evaluation. He occasionally gave lectures at Soviet technical institutes about lessons learned during the war, and he always talked about the Panther examination as a formative experience that shaped his understanding of engineering principles. The sophisticated German tank had taught Soviet engineers more through its failures than through its successes, validating approaches they had pioneered and confirming that practical effectiveness mattered more than theoretical perfection. The Panther that Soviet engineers examined so carefully in 1943 remains preserved at the Kubinka Tank Museum outside Moscow, maintained in running condition and occasionally demonstrated for visitors and technical students. It sits among dozens of other captured German vehicles, a testament to Soviet success in the war and a reminder of the lessons learned through careful examination of enemy equipment. Visitors today can see the complex interleaved suspension, the sophisticated gun systems, the precision-engineered components that made the Panther simultaneously impressive and problematic. The sign beside the preserved Panther at Kubinka includes a quote from the original 1943 examination report that captures the fundamental lesson Soviet engineers drew from studying the vehicle. The enemy has created a tank of impressive technical sophistication, but questionable practical value. Our own simpler machines, while less impressive in specifications, are superior in the qualities that matter for sustained combat operations: reliability, ease of maintenance, and suitability for mass production. This examination validates our design philosophy and demonstrates that victory belongs not to those who build the most sophisticated weapons, but to those who build weapons their forces can effectively employ in sufficient numbers. That quote, written by Soviet engineers in 1943 after 3 months of intensive technical examination, summarized lessons about military technology and engineering philosophy that remained valid throughout the Cold War and continue influencing military equipment design today. The Panther examination revealed fundamental truths about weapon system effectiveness that transcended the specific technical details of 1940s tank design. Sophistication without reliability is useless. Complex systems requiring extensive maintenance fail under combat stress. Manufacturing difficulty limits numbers, and numbers often matter more than individual quality. These lessons, learned through careful study of a captured enemy tank, influenced Soviet military thinking for generations and represented one of the war's most important intelligence achievements, even though it involved no espionage or secret intelligence gathering, only careful engineering analysis of captured equipment.